Okay, we are ready. I'd like to see the translation there, if it's picking up correctly. I was wondering if it will recognize my accents, and there is one word that I want to see, if it picks Akka. No. When I say Akka, it's A-K-K-A. Now I will say Akka. Okay, I fix it. I will say it a few times, so make sure you write it correctly. Or maybe it's someone out there writing that, I don't know. Okay, let's start it. By the way, I've been nominated, or this talk has been nominated for the award for the title with more buzzwords. So happy you're here to watch this talk, to attend this talk. So, resilient applications, agentic AI applications, what does that mean? And the whole thing is about this conference is that the time for agentic AI is here for us Java developers. And lots of people are still learning. I think there are lots of concepts that we are all learning and hearing about. I will not go completely in detail what is an agent today. I hope there are other talks in the conference that will explain that to you. A conference is never linear, no? You never start from scratch, first concept and then the second. Things come. At the end of the week, I hope you have enough information, the building blocks will start to fit, the ideas will start to connect to each other and so on. Because I will talk a little bit about agents, but there are other talks that will be go more in detail about agents. So I'd like to talk a little bit about Python. Lots of Java developers are hearing that they need to learn Python. Well, I don't think it's the case, at least not the case anymore. We're going to talk about some patterns in agentic challenge problems, how that thing will break, because things will break. We need to learn how to build agentic systems. Then I will do a deep dive in Akka to explain a few core concepts that we have, so you can understand why that basic architecture, that core principles that we have built in Akka can help you build resilient applications. And I'm not talking only about agentic applications, general applications that are self-healing and resilient. And then I have a demo where you have, actually, I don't know if you have been at our booth, we have very simple agentic flow. It's more for the fun. We generate haiku poems. And in itself, it's not a complicated flow, but we use for the booth. I will do a demo here, but the demo is more to show. Well, I will show the code, so you have an idea how it looks like how to build an agentic system in Akka. But the goal of the demo is to show how Akka can make it resilient. So let's go. So first, let's bash Python a little bit. So Python is great. I don't like to bash other languages, although I'm not a Python developer neither. I think I can improve my Python skills as well. But they have a nice ecosystem for many things. They are very, very well known in the AI world. For training model, for doing experimentation, there are a lot of libraries for that. But that is one side of the story. We have TensorFlow, PyTorch. Everybody have ever seen Jupyter Notebook. It's like a web interface. That's nice to train models to get your algorithm correctly, but that's not application development. When you get to building enterprise-grade applications, you have other kind of technologies. You need other kind of technologies, and there are many things that you can use when you argue at your organization about Python, trying to defend your Java skills. You can search about, there are so many things. First is type safety, problem with how you build and deploy, compatibility. Java, we know it's a much more solid technology and platform and ecosystem for that when you're building business applications. So agentic AI, so there are two sides of that story. One side is training the models. People at OpenAI, they are doing lots of Python because they are training models. People doing general artificial intelligence or machine learning, they are using Python and so forth. But here we are on the other side of the story. Here we are the clients, in the sense we will use the models that those people are training to integrate in our applications. So our applications are just Java applications that we will use LLMs or small language models as well. So here we don't need Python. And there are lots of libraries nowadays in the Java ecosystem. Akka is one of, it's more than a library, it's a full platform. We use LangChain4j, for instance, internally. And there are many other options. So you don't need to learn Python. So what is an agent? There are many definitions. I will bring mine on. I don't know, there was a thing in the Scala community, because in Akka we do lots of Scala, and there was a thing that everybody has a definition of a monad. Well, now in the new world, everybody has a definition of an agent. So this is my definition. That's how I see it. So agent, it's just think like an object that you create yourself. And the first thing it has, it will talk with a language model. It can be a large language model or a small language model. And to start with, it has two things. It has this, what we call the system prompt, which is kind of basic description of what this agent should do. And that is sent to the LLM. You can put everything. You can say, you return when you answer back, you need to answer back using JSON format or Markdown, or you should avoid answer questions of that type, or you should only answer questions about the weather, for example. So this is the system prompt, like the basic instructions that you give to it. And then you have the input query. And here can be a user, like in a chatbot, but can be any other thing, that any other call coming from Kafka, some process in your system that just call the agent at some point. But if it's only talking to the LLM, it's not doing things, and the word agent refer to that. So it needs to be able to execute other things. So the agent will have access to tools. It can be just functions. It can be service that you call through REST APIs. It can be MCP servers. I will not talk about MCP. There will be other talks here about MCP, but think about that as a service somewhere that you declare and you give to your agent. So the agent has those tools, and it will call the LLM, and the LLM, same, I give an example. You ask for booking a hotel, and then that agent should have access to a booking hotel API. The LLM will know your preference, and then will do first tell back to the agent, well, I need more information. You need to call this API that you told me you have, call it, and come back. So the agent goes and call that tool, collect more information, and go back to the LLM, say, okay, here's the information you asked me. And the LLM reason a little bit and ask, okay, I need more information. Can you call that other method now? And then the agent goes and call that other method. So sometimes you're going to hear people saying, you have MCPs or tools, and the AI will call it. No, the AI will never call it. It's the agent framework that you're using that will do that for you. So the AI, the LLM will give the instruction, will respond saying, I need this tool to be called. And the agent, the framework you're using, will do that call for you and go back to the LLM with the results. And then there is also RAG, which is retrieval augmented generation, in which you have a set of documents and the AI is not aware of that. So you first search those documents, collect some data, and you feed the AI with those extra data. And you also have the context memory, because your agents, you have conversation with the AI, and you accumulate information, and all that is important. So in all that example here, in all those cases, it's about context. You have the memory is a context, RAG, when you're collecting data from some other external documentation, that's context. The tools, they need to be well documented, because it's not enough to just write a nice method name. You need to describe what the method is doing. You're going to see that all frameworks here, not only Akka, but everybody is working with annotations to describe what the method does. Why? Because that information goes to the LLM, is the information that is in the annotation that you document that goes to the LLM. So you are creating context, so the LLM can make decisions and choose which tool to call and how to answer back. Everything here is about context. And you can build an agent and give all the tools you have to it, but that's not ideal. Because if you give too much, if you create an agent with a very broad scope, it will not be efficient. It will give bad answers, actually, because first you're going to be sending too much information to the LLM, you're going to be paying for that, and the LLM will not answer in an optimal way. So the best thing is to create smaller, specialized, small scope agents. And those work better. So by doing that, you end up having very different agents in your system that you have to compose, orchestrate, and make them work together to produce your result. And then things start to get complicated. Because, well, there are a few patterns, and there is a very good blog from Anthropic, which is the company behind Claude, and Microsoft also wrote a very good one about patterns in agents, agentic patterns. And the most common one is the chain. You just have 3 agents in that example here, and you know, okay, I call the first one, it will produce some results, it will call some tools. Now I have something. I go to the next one, I pass the information to my second agent. It does call tools, do some more reasoning, and further and further. That's the easy one. You can also have parallel. You can get some input and then say, okay, next thing is I need to call those 3 agents, and I don't need to do it sequentially. I can just do in parallel, and meaning that I have to wait for the results of the 3 agents in case here, and eventually I take the results and I build my final result, passing or not, by passing it to another agent like a summarizer, or maybe just not, just returning all 3 results together. There is the router. You receive a message, the router decides who has to receive that. It can be a decision made by LLM. You tell the LLM, okay, look, I have those 3 agents. That's the question. Which one should I call? And an AI agent will say, okay, call the 3rd one. Or it can be just an if and else. You have something on the payload that you are able to easily, and better if you can do that in code, don't use a LLM for that. But if you have information in the payload that you can immediately see which one you need to go, you just route. But you have this idea of selecting the next agent dynamically. Another one, which I find very interesting, is because all those agents, they connect to LLM, and you can have one connected to OpenAI, another one connected to Google Gemini, for example. So you can also have a system where you get input, and you have 3 agents, one using OpenAI, another one using Claude, and another one who's using Google Gemini, and you send to them the same input. And you wait for the 3 results, and then you ask for another agent, which is the judge here, and say, I have 3 results here, what is the best? That was my question, and I got those 3 results. the three outputs, which one is the best? And that other agent will say, okay, this one is the best one, let's select this one. So you use AI to judge if what is the best output. You can also pick two of the two best outputs and summarize again. And that example here, you can already see that things can get very complex. And when we are doing demos, and our demo in the booth, it's a simple thing. But the real systems, they grow, and they become much more complex than just small flows. And they are a combination of all of those. Routing, parallelism, judgment, chaining, all kind of stuff. And the thing is, all those calls to agents, all those agents, at some point, they will call a language model that is probably a large language model that is probably not running on your hardware. It's running somewhere on the internet. Those things will time out. Not only the call to the LLMs, but the toolings. Maybe you're using a tool that is down for some reason. You're using a service that is not available. And the agent will fail because of that. And they can fail for other reasons, hardware problems. The JVM where it's running may be shut down. You may be in the middle of a rolling update where you're replacing your application, and in the middle of such a flow, your JVM goes down and needs to be restarted. But one thing is for sure, all of that will consume money, and all of that will consume tokens. So what happens when you are in the middle of this flow and something crashes? You want to restart it, and you don't want to restart from scratch because we're going to pay for the tokens again. So you need a system that helps you to restart from where you stopped. And that is what we call durable execution, where you have kind of system that is able to create checkpoints of a process that will save those checkpoints. And if something goes south, the system is able to resume from where it stopped. So here we are resuming from the point where we crashed, let's say. Now, how can Akka help you on that? So one analogy that I like to give when people ask me to explain Akka is that the JVM is well known by us as a managed runtime that gave us lots of things. It's memory model, concurrency primitives, garbage collection, things that C++ developers were struggling. Back in the time, they are still, because they stay in C++, but we moved to Java. So it's a runtime that manages that for you. And by doing that, it increases your capacity of building software, because now you don't need to think on all those things. You don't have to spend time on those. Well, Akka is a runtime built in Scala and Java on top of the JVM, but it solves another level of problems. The problem that Akka solves it's about distributed systems, scalability, and resilience. That's what Akka does. And Akka, the whole idea is based on the actor model. It's a computational paradigm, let's say, where we can introduce in the system what we call location transparency. And that is fundamental. The actor model gives us location transparency, and that's fundamental to build resilient systems. So what is an actor? So think that as just an object. It has state and behavior. Let's start with that. But there is one difference. When you are building a Java application and you create an object, you can do new, my object, and you call methods. Well, in Akka, you can't. When you create an actor, you cannot initiate it yourself. You have to declare it to Akka, and when you want to change something on that object, you have to ask Akka to do that for you. So you kind of delegate to Akka the task to initialize your object and deliver and call the method you want. Internally, it's about message passing but in the new APIs that I showed today, it looks like it's a method call, but in a special way. I will show later. But for now, let's just to understand how that works. Is at some point you want to call a method on that object that your actor, but you cannot access it because Akka is doing that. So you ask Akka to do it, and the commands that needs to be sent, they are put on a mailbox. They get on that mailbox in order, and Akka deliver them to your object in the order they arrive. And that is what we call location transparency, because you don't know where are your objects. When you do new inside a method in your Java application, new something, you know exactly the scope of this object. You have directly reference to it. In Akka, you don't. So location transparency is because it's not visible to you where is this actor running. Now, I will get why is that important? No? So imagine that you have, I here have a cluster of one node, which is not a real cluster, but bear with me, we get there. So let's imagine that you have 3 commands coming in, one for actor A, for B, and C. So it arrives in the system, in your application. It can be an endpoint, and then you want to call that actor. You go through the actor system. So you pass through the actor system, and the actor system delivers the object to the objects, to the actors. Now, let's say that I add another node. I scale out my application to 2 nodes. And when we talk about clustering in Akka, it means that those 2 JVM nodes, they are of course the same application deployed twice, but they talk to each other. There is a handshake between them, and they form a cluster. So they know that they have siblings. So what's going to happen here is that node 1 will say, well, I have a new friend here, and I can give it a few actors so I can use less resource. So actor B and D, according to our algorithm, will be just moved to the other node. Now, the requests arrive, and as you see, node 1 receives B, but B is on node 2. And node 2 receives C, but C is running on node 1. Well, because it goes to the actor system, and the actor systems are aware of the nodes, they delegate. The first one, it's on the same JVM, just as easy. For command B, it delegates to the other node and back. So you don't know where what the location transparency gives to us is the possibility to scale out our application. And because Akka is controlling the life cycle of those actors, objects, let's say, we can move your computation horizontally. We can scale the JVM horizontally. And everything in Akka is built on top of this abstraction. Everything, that's the most basic construct that we have inside Akka, the actor model. So agents, they are built on that. Workflows, they are built on that. So agents and workflows in the new Akka SDK, they are components. In the new Akka SDK, you don't work with actors directly. You have those high-level components, and they all have some special some capabilities. No? So the workflows is about durable execution, agents is about calling tooling and LLMs and so on. So there is also event source entities and key value entities. There are entities like in domain-driven design. And persisted. No key value, it's like key value. Event sourcing, it's event sourcing. So I will give you some examples. Oh, I have plenty of time. I will relax. And I know now that I can do my demo relaxed. Oh, good. So back to context. No? This is just an example. And agentic flows, they can be much more complex than that, of course. But I picked that example because it will give us it's small enough to fit my slide, and it it shows you all the pieces that you need. So imagine the following situation. You have a system that have all kinds of agents, like hotel booking, flight booking, train, or summarizer agents, activity agents, and so on and so on. I do a query to this. I post something saying I would like to make a trip to Amsterdam. I don't give much information, but I'm a user and I have a profile. So the system knows, by the way, I live here in Belgium. So the system knows that I'm not so far from Amsterdam. The system maybe know that I prefer train than flight if it's for short distance. So because I just said, book me a trip to Amsterdam, the planner, it can be based on AI or just other kind of planning algorithm, will select the agents that I need to use. By the way, if you're using agents to select other agents, you have to treat your agents like tools. You have to describe them. They have to have annotations that describe what they are good for, when you should use them. So all of that are kind of metadata that needs to be there so the AIs can select things. But this planner could also be just some other planning algorithm. But let's continue. Let's say that this agent decides that it will pick the hotel and the train booking agent. And it selects, and it will eventually decide the ordering. Because, for instance, it's better to first book your train, because there are more hotels in a city than available train seats. So book first the train. If you book the hotel, for example. In that process, each of those agents, the question is, do they need to know what the previous agent did or not? And very, very often, yes. For example, the hotel booking agent, if the train booking agent booked a train that arrives in Amsterdam at 11 o'clock at night, then the hotel booking agent may decide to book something close to the train station. Or if, for instance, I have a foldable bike, if the system knows about that, they'll say, okay, doesn't need to be close to the station because this guy can take his bike. So all that information is fed to the agents from your profile, but also one agent needs to see what the other did, or you have to explicitly pass to it each time. So there is this idea that you create a conversation between the agents so they can see what has been said so far, so they can make decisions based on that. So there are two important concepts. One is, how can my application be durable, and how can I feed my agents with enough context? And the conversation is one of them. No? So you can imagine that in that flow, we start with one agent, the planner, and the first thing that we recommend to our customers is to always use their agents with workflow, because of workflows, Akka workflows give you durable execution. So in that case here, we ask the planner, look, that's what I need to do. Those are my agents. Select the agents and in the right order for me. So the planner will do that task. That information goes to what we call the session memory, which, by the way, it's event sourced. It's auditable. You can subscribe to the events and take other actions if you want, or evaluate your agents and so on. And so it will save that conversation. And when it finishes, it will save the state of the workflow. If you have a state, you can put a state on the workflow. It's saved. And then you have to tell, okay, what's next? What is the next step? And for the next step, you probably have some input. If you have input for the next step, this input is also saved, serialized and persisted. If that workflow breaks now, it will restart from that point. Because number 3 here is the checkpoint, is where that task is considered completed, and we save what is the next thing to do. And then let's say that we go to the next step, and then things will repeat, except that here, first we're going to read the conversation so the train booking agent can see what the planner said and do his stuff. Now, by default, all agents in Akka participate on a session. You don't have to participate on the same session. It's just an ID that you choose for your session, so you can choose different IDs for each agent so they don't see each other conversations. And you can also configure an agent to only read, only write, or just ignore the session. But you do have to give a session ID. So you can just give anything and just configure the agent. No, you don't read, you don't write, you just work with the input that you get. So you don't get information from the memory. That's your choice. You choose how to do that. So the workflow just goes and each step is executed. And before that, they are before moving to the next step, the description, what needs to be done next, is persisted. Well, and then and when you get the summarizer agents, you tell the workflow, I'm fine, you can stop now because it's finished. So 2 things, durable execution. Agents run inside workflows, so you have durable execution, distribution as well, because Akka it's all about distributing the load over the cluster, over the nodes in your cluster. And you have session memory, so you can preserve the memory between the execution points and the agents. Now, one more thing, because this is very different and very special, is that in the new SDK, you have components. I said that you don't use actors directly, you use those high-level components. And your code, when you write an Akka application, it gets embedded inside the Akka runtime. And the Akka runtime controls everything there. All the execution, the lifecycle of your actors or components. And each time that you call a method, your method will return what we call an effect. An effect, it's like, of course, inside that method, you can run code. But the code that what matters is what you put in the effect. The effect is like a lazy computation. And it's a description of what needs to be done. So it's you telling Akka what Akka needs to do. And each component has returned a different kind of effect. So, for example, a workflow component, it returns an effect that has transition, that you can say, save my state and transition to this other method. That's one type of effect. Event source entity has another kind of effect that is, those are the events that I want to get persisted. And once they get persisted, you need to apply them to my state. And after you do that, you reply to the caller of that method with this result. That's another kind of effect. And that is lazy. You build it, you return that, and Akka will interpret and execute it. I talk and I forgot to do the bullet points. But that is very important because the effect is what allow us to control the execution of all that code and be able to know what is happening and be able to distribute that as well, because I can have the save points, for instance. I can define exactly how this will be executed in which thread pool, for example. And here's the coolest thing, I think, is that recently we added support to virtual threads. Actually, it's when we built the agent, we said, now we really need to have support for virtual threads, because people will really be going over the internet now. They will really be calling LLMs over the internet, and that is blocking calls, and we don't want blocking calls, uncontrolled blocking calls happening like that inside the components. So every code that runs inside the components run in a virtual thread thread pool, optimize it for you using virtual threads. So you don't need to use futures anymore. You just do general calls. It gets blocked, yes, on the virtual thread, and Akka does all the machinery needed to get this running smoothly. Okay, no takeaways, codes. So first, no code, and here. I will start, I close them all, because I will start showing the Haiku agents. I think this one. One other thing that you're going to see in many frameworks, there are, in the case of LangChain4j, for instance, there are two ways of doing. There is the programmatic APIs, and there are the annotation-based APIs, where you create an interface, you put annotations, and LangChain4j will create the class at runtime based on the interface. We decided not to use that for two reasons. We use the programmatic behind the scenes. We use LangChain4j, and we decided to use the programmatic APIs for two reasons. The first is that we got a few requests from customers saying that they would like to decide which system message they want to use depending on the payload, on the input. So depending on, here it's just a string, but people build domain objects, they pass, and depending on the content, they decide what is the system message that they want to use. And then sometimes they just want to run some code and then call the agent. So here, my system message is just hard-coded. Another thing that you can do is there is an entity where you can put the versions of your system message, and at runtime you can change the system message. But I'm not demoing that today. So just you can check that later eventually. So here, for instance, I have my system message, I have the input from the user, and I'm telling the effect here that the type needs to be a Haiku, which is just a class that I have. A Haiku has 3 lines, so it has 3 lines and 3 lines of text. No. Here. And as you see, I'm not doing anything yet. I'm just describing. That's my system message. That's my user message. That's the return type of this call. And then I reply. I didn't execute it. I just describe it. So the effect here is passed to Akka, and Akka will execute it. And we'll do add tracing and all the magic that Akka needs to do to have that working, and run it on a virtual thread. So the whole method here will be running on a virtual thread, including the call to the LLM. The LLM is not being configured here because we have a configuration. The LLM is configured here. Actually, I'm not using OpenAI anymore. I don't know, I should have replaced it here. Is this one that is being used? Yeah, here you can see that's the default provider. So in all agents in that application is using that one. I can delete this one actually. Boom. So all of them are using this one. You can also configure you can configure it by model. You can provide a model programmatically. You can also provide it from configuration. You give the here you can. There are a few that you can configure yourself, and you can create your own provider. So each agent can have its own provider, the model provider, and you configure it here, or you configure one for all of them in the configuration file. Okay. Workflow. Workflow is much more complex, let's say. I show this one. Again, it's a class. You implement it. you need to have those annotations. That's how Akka will identify the components and so forth. And the workflows is special because it has two kinds of effects. Because a workflow, it's open to the external world, so you can call your workflow from some other part of your code, and there is a kind of effect for that, and there is the transitional effect that we call the step effect. It's the only component we have that has two kinds of effects. So here's the start method. So to start, you don't have it in memory, so you have to assign an ID to it and say, okay, I want a workflow, that's the ID, I will call that method. And here it says, okay, if it's already running, I just return done. If it's not running, I will save my state as running here. That's my state. My state is configured here. It's very simple. It's just the ID of the talk. Actually, it's the haiku, actually. I need to fix that. And false is running or not. It's just a small state that I have here to control a little bit. And then I tell here on the effect and say, that's what needs to happen. First, we're going to save the state, and then we're going to transition to fetch talk. I'm on the wrong one. That's why it's talk ID. I'm on the wrong, it's this one. Okay. Start. It's the same thing. It's a workflow. This one. If I have a state, I will just log already running, in progress, is done. Otherwise, I will start it. And what I do here, I save the state for the haiku. And then I say, check the quality of this haiku. It's the next method. And as you see here, and that's special, as you see, I'm not calling the method. I'm passing a method reference. Because what I'm doing here in the effect is that I'm instructing Akka what needs to be done next. I'm not calling that method. I'm just telling Akka what needs to be done next. So I pass the message reference, the method reference here, and we do a little bit trick to know what is the input type of message, check message quality. You see that is user input. If I go back, this will not compile. So the with input is based on the input of this method here. So it's type safe. No. So what we do here is we tell Akka, you save the state. When you finish, you transition to the next method. And what is from that point here, that's the input that will be persisted. So if that workflow fails for some reason, it restarts knowing what is the next step that needs to be executed and what is the next input that needs to be passed. And then we just go further and check message. That is one agent to detect harmful language. Some people at the booth said, yeah, what if I write something ugly here? And I said, no, we believe it will be blocked because we have this detector that will judge if the language is acceptable or not. And then from here, what we do, next step, analyze the sentiment. Because a haiku, it's a positive thing. We want to have positive things in the booth as well. And also we send to the speakers each time before the talks, we send a haiku based on their talk content. We create a haiku and send to them. So if it's positive or neutral, we send. If it's negative, we don't send. And so here I'm just chaining those. It's a very simple agentic flow because I just have one after the other, very sequential. I don't really need memory in that case here. But I do want to have durable execution. And if it's negative, I will reject it, and then I go and I generate the haiku. And as you see, when I call, that's maybe good to reinforce. Here, wait a minute, here, generate haiku. Look at that method. First, I came from here. That's the step effect in which I tell Akka When you finish that step, you execute that other step, which is that method, defining that method with this input. Great. And if you look here, again, I'm calling my agent. So as you see, I cannot initialize the agent myself. I have to use this component client, and I say, I want a component client for the kind of, the type of component, it's an agent. It's participate on that session. And here's the method that I want to call on that agent that I don't know where it's being initialized. It's not on me, the user of Akka, to know that. And that's the input. So as you see, I cannot initialize my agent and call it. I ask Akka to do that. So there is this interaction, the component client, to call that method wherever this agent is initialized. Akka is controlling the lifecycle of the agent. Okay, how many time? Oh, okay, now I'm running out of time. No, I think we are good. So I have here, okay, now demo is dangerous because I don't want to make a mistake now. I will start 2 nodes. Okay. Let me just compile that to make sure that. Okay, I'll start this one. On top, I'm starting node 2. So I'm running that on my machine because it's much easier to fake a failure and crash a node than to run it on our platform. By the way, I didn't mention that, but so you have Akka libraries, low-level concurrent abstractions, actors, and so forth. And then you have Akka SDK, which is components. And we have our platform where you can deploy your application. But if you want to know more, come to the booth, because I will not explain all that during the talk, because I can talk about that for hours. So what we're going to do here is I will start 2 nodes. They will see each other. They will form a cluster. But the node 2, I'm giving a rate failure of 1, what's 100%. So what's going to happen is I will create some haikus. And at some point, I will send the request to node 1, okay? But Akka might decide that the workflow that needs to generate this haiku that I will request needs to be initialized in node 2. I cannot control that as a developer right now. It's built inside Akka. So Akka will do that. So if it goes to node 1, it will work, I hope. If it goes to node 2, it will fail. And that's the demo that I want to show, because I want you to see it failing in node 2. So I will shut down node 2. And then the node 1, the survivor, will say, OK, so this workflow needs to be reinitiated here because it crashed in the middle of something. So let's see if now I didn't check. Yeah, I have. I need the internet because I will use the LLM, no? So, don't scan that QR code. Aha. I know why. Okay. Because I didn't start my Docker. Node 1, node 2. So usually when you're developing an Akka application, you don't have a database. You use in-memory database. But for the demo, because I have 2 nodes, I need to have a database. When you deploy, of course, you have a database. So as you see here, there is one started in port 9001, and 9,000. I go, okay, here, don't scan this QR code because it's my local machine. So you can, but you'll not be able to do anything. Let's write something here. I'm doing my demo at my Akka demo at caramba, at Devox. Yeah, when you then your language come, your real language come. Caramba. Okay. So it's going, takes a while. We need to watch here. Okay, node 1 took it. That's not what we want. So let's just generate another one. I hope that node 2 will take this one. Please, Akka, help me now. Lots of people are watching. So the thing of this demo I revert is it needs to fail. The demo needs to fail. So it doesn't fail, I'm in trouble. But it's failing. So node 2 got the task. I will just kill node 2. I hope I killed the right one. Okay. And node 1 took over the workflow. I can show here that this is the token that was the Haiku ID that was created. It was failing because I configured node 2 to fail. And then when I remove the JVM, the other node said, okay, I lost my friend. There was something running there. I can preserve that information and it restarts here. So that's what's gonna give you in your agentic flow the guarantee that once you start it, it will come to completion. But there are a few more things related to that. I think I have my Haiku here. Well, it's there. So I'll go back to the presentation. That was the demo. But I want to talk a little bit about that because we often think about the agentic system as a chatbot. And in our case, here is the case. You have a human being writing something, and as you see, I send a message to the user, to the person on the other side, kind of entertaining that person because LLM call, and here we are doing 4 calls. LLM call takes time. You see that it takes time. If you go to the booth and try it out, you see that we are talking about seconds. And when you are building this kind of interface, like with a chatbot, you need to entertain the user. But most systems, agentic systems, are not built like that. They are background process happening in your application. Something happens in your application that triggers a flow. Typical scenario, you're listening, picking message from a broker. Think of Kafka or something else, PubSub, Google PubSub. If every time that you pick a message from such a broker and you need to start a flow, even if it's a small one with 3 agents, it will take time. And you cannot commit on the broker saying that you pick that message until you finish. So it means that you have the head of line blocking now on that queue, on that broker, because you are running an agentic system. So when you have this situation, you're going to have a huge Kafka of broker lag message that needs to be processed out there waiting. So you cannot pick the message, start your flow, and pick the next message because you need to have a guarantee that this message will be processed, unless you don't care. In some systems, you just best effort, you pick, you try, doesn't fail, okay, I pick the next one, I don't care. Then you're fine. But if you need to process all of them, if you need to pipe them into an agentic system each time, you need to be sure that first, you're not blocking your queue, and secondly, that this process that you started will complete at the end, will come to completion. So for that, you need to have durable execution, being that workflows or something else. But you need to control that. And that's what will give you the resilience that those systems need. Because then you can go to that topic, you pick the message, you give to the workflow that has durable execution, it goes executed, and you can pick the next. And then comes the next problem. If you're picking lots of message and building agentic system, running an agentic flow, calling LLMs and so on, and blocking and so forth, how that system will behave? At some point, you'll come to exhaustion. At some point, we'll have too much open connections, too much blocking, and so forth. With virtual threads, we solve it. That's one point. But we still using lots of resources in such a flow. And that's why Akka, if you take such a system, Akka, when you deploy in our platform, the platform monitor that, and then when it sees that you have, let's say, by default, you get 3 nodes. If the nodes are under pressure, we scale to 5, eventually 15, depends on how is that configured. And then we scale and distribute the workflows. They break, we stop them in the middle of the execution, but it's not a problem because we know that we can restart from where we stopped. So you have a node with we have a cluster with 3 nodes, lots of workflows running. You need to shut them down, a few of them, to spread the load, and we restart it. So that's what I call, that is what is possible when you have durable execution, when you have location transparency, and so forth. I think I passed my time here, so I will just go quick to the takeaway. Very important, everything is about context, how you describe your tools. Your domain is context. The classes that you use to fill with data coming from LLMs, those are context. The memory, you need to have infrastructure to share the conversation memory between your different agents. Durable execution, we have workflow states, there are other solutions. I think ours is the coolest because you can scale out your application and the workflow goals are moved over the clusters and over the nodes in the cluster. But most important, you need to have that under control. You need to control your agents. You need to know what it's doing. You need to have them monitored, to have traceability, of course, but you need to build the systems that are resilient and are under your control because they will cost you LLM tokens, no? And durable execution is will really cut on token consumption because you don't need to repeat work when things break. So, of course, Akka.io is our website. You can scan here. Build your first agent. It's a tutorial we have. There's a little bit of theory. If you're on that page, you start understanding what are the components that we have. And there is a Hello World example that you can start playing around. It's not a real agentic system, the Hello World, but what is nice is that it's like a game. You say hello, it answers in another language, and then each time that you talk to the agents, so it preserves the memory, and the idea is to show that, and so it always answers in another language to show that. And the idea is that it should not repeat a language, something like that. Anyway, thank you very much. I don't think we have time for questions.